Hello, Tyler Kranz here over at NWS Bismarck. This presentation I'm just going to cover my results I recently obtained from an MRMS MESH verification study I've been working on over the past several months. So before we get started, I'll let you guys know what the overall goal of my study is. Basically, I'm just trying to quantify how well the mesh product is performing, and then identify days when mesh is performing poorly, and then analyze the environment on those days along with the radar characteristics of each thunderstorm. And each thunderstorm event was actually analyzed manually for this study. And then most importantly, I'm trying to determine if there's any operationally useful trends that are evident, because if so, that could be really useful during severe weather operations for not just our WFO here in Bismarck, but for pretty much any WFO that deals with severe convection and uses the MRMS mesh product. And I know most WFOs are using that nowadays because it is truly a great tool, and I will be showing how well it typically performs in this study. So anyways, before we get going, it is important to remember how the mesh product is actually calculated. It's simply just the square root of the severe HAL index. And if you can recall, there's basically two inputs to the severe HAL index. The 3D reflectivity cube, so basically your observed radar data, using all the available radars that it can, and then your vertical temperature profile from the operational RAP model. So that's worth remembering because sometimes it's easy to forget that the mesh product does include some model data. It isn't 100% observed data making that product. So my methodology that I used for this study is actually pretty simple. All I really did was compile all the official HAL LSRs within the Bismarck CWA from May through September for the summer of 2018. And I got those LSRs from the NCEI Storm database. From there, I was able to overlay the LSR reports onto the corresponding mesh tracks, and I used 60-minute mesh tracks for this study. And to actually display those tracks, I used the Weather Archive and Visualization Experiment. If you guys haven't used that before, I highly recommend you try it out. It's a really neat tool. It's got a lot of great data in there. Awesome for doing research or case studies, or even stuff like posting to social media or creating weather stories. It's useful for that too. So if you haven't checked that out, I highly recommend it. This study wouldn't even have been possible without it. Anyways, and then my last step was to manually record and compare the mesh HAL size to what was actually observed at the ground via the LSR. And then I kept track of everything in Microsoft Excel. And I also made sure to record the max value within the entire 60-minute mesh track, mainly because that's oftentimes what we use to craft our wording in our severe thunderstorm warnings or tornado warnings. We oftentimes are trying to message what we think are the largest possible hailstones within the storm, which is basically what the core of a mesh track would be trying to show you. So here's a quick visual example of my methodology. So imagine this red star is a storm spotter called and reported quarter-sized HAL right here. And then we went in and sent an LSR for that. And that's great because it made this study possible, because from there I was able to directly compare it to what mesh had at that same time and location of the LSR. So that was recorded, and then like I said earlier, I would also make sure to record the max value found within the entire 60-minute mesh track, which in this case was a bit over 2 inches. So after compiling all of this data together, I was able to come up with a few numbers, and so you can really just get a gist of how well this mesh product is actually performing in a quantitative sense. So In this study, I have 175 LSRs total that I analyzed, and those were all manually compared one by one to their corresponding mesh tracks. So the methodology is pretty simple, but it is rather time consuming, and for that reason I have only been able to do it for 1 year's worth, or one summer, the summer of 2018. Future work, I would like to extend that into 2019, but for now I'll discuss my results from 2018, and I did that for the Bismarck CWA. And there ended up being a total of 35 different days where there was at least one HAL LSR. So basically 35 days were analyzed for this study. Anyways, out of all 175 LSR to mesh comparisons, I computed the mean absolute error, and it came out to just 0.32 inches, so about a third of an inch, and that's really impressive. So basically, in other words, mesh is performing really well on average, which goes to show, you know, how great of a tool that this product really is. So it's no wonder WFOs across the Weather Service are using this product quite heavily nowadays in their severe warning operations, which they should be. With that said, there are select days and select certain types of environments where mesh is performing poorly on a consistent basis. So my goal is to analyze the environment and what the radar characteristics looked like on those select days where mesh performed poorly, to see if I can identify any operational trends that can really be helpful for you guys during your severe weather ops. So we'll start with case study 1. This occurred in late May of 2018, and on this day the mesh product was reading too high, so there was a high bias on this day. And so just to give you a quick idea of what the surface weather was like on this day, we had surface temperatures in the 60s for the most part west of this stationary frontal boundary across western North Dakota, and then across central and eastern North Dakota we're stuck in the upper 70s to lower 80s in the far east, and you can kind of see hints of maybe a convergence zone going on right here across southwestern North Dakota. And if you're looking at the environment from the standpoint of the NAM output on this day, drawing our attention over here to southwestern North Dakota, you'll see that we had modest CAPE on this day. Surface CAPE values were generally around 1,500 to a little over 2,000 joules per kilogram, which is decent, but you'll notice over here our shear was rather weak. We're really only seeing about 20 to 28 knots of effective bulk shear from 0 to 6 kilometers, so not a whole lot. And at 500 millibars, it does appear that there's this weak wave. And then lastly, in this bottom right panel, you'll see that there's a hint that maybe the southwest part of the state is near the left exit region of a weak upper level jet. So brief summary of the environment on this day. I would classify it as a moderate CAPE but low shear day with weak synoptic scale lift and at least some mesoscale forcing along that quasi-stationary surface front. And one thing worth mentioning related to the expected storm mode, the shear vectors on this day were oriented nearly parallel to that surface front, which would tend to suggest any initially discrete cells may quickly congeal and become more of a multicellular cluster of storms, which we all know would tend to mitigate the chances of receiving giant hail because you'd prefer a more of an isolated discrete storm mode for that. But anyways, these two plots I recreated actually from a paper. They're directly from a paper done by Johnson and Sugden in 2014. So I just simply recreated two of the figures that are in that study that I find really useful. All I really did was change the units of what they had. They had it in meters per second, and I just switched it to knots because that's what we're used to dealing with when we're forecasting. And then over here we're trying to relate MU CAPE to HAL size. So basically this is just A quick box and whisker plot you can use to kind of get an overall sense of a range of hail sizes that you would expect given your environment based on the MBU Cape and the effective bulk shear from 0 to 6 kilometers. So for May 28th, you'll notice that with Cape values generally around 2,000 joules or less, we were kind of favoring this 0.75 inch to 1.25 inch hail. And then over here, remember we had pretty weak shear on this day, around 25 knots or so. So once again, we're favoring hailstones between the size of about nickels or so to about $0.50. So nothing crazy. We wouldn't really expect giant hail on this day, maybe 1.75 inches at most, but receiving hail greater than that, say 2 inches or larger, seems really unlikely given the environment we have. So here's a radar loop on this day. Focus on this cell that moved directly over the town of New England, which was good in the sense that we were able to get a storm report out of it and get an observed hailstone. And then I was able to directly compare that to what MESH had on this day. So if you look at the MESH tracks for this storm, you'll notice that it picked up all the way to at least 1.5 inches there, drops off a bit, and then goes back up as that updraft intensifies again and the storm pulses back up. Right there, MESH was suggesting giant hail over 2 inches in diameter. So right off the bat, you would maybe want to question that a bit, seeing as though our environment really wasn't supportive of giant hail greater than 2 inches. In general, it was supportive of hail less than 1.75 inches. So if you looked at dual pole signatures in addition to that, you would notice that giant hail does not look likely based off your dual pole characteristics, mainly because your CC values were rather high, generally above 0.9. We know for giant hail greater than 2 inches, like MESH was suggesting, we would generally want to see lower CC values. And then our KDP values in general were pretty low, where the hail core was around 0 to a little over 2 degrees per kilometer. And ZDR values were low too, generally less than 0. So here's a little checklist that you can use to relate dual pole characteristics to hail size. And what you'll see is for this storm, we're most closely matching severe hail mixed with rain. And that's important that it's mixed with rain, because what I think is going on is MESH is tending to overestimate these pulsy air mass thunderstorms that have vertically upright updrafts, and maybe aloft the hailstones are bigger than quarters like MESH is suggesting, but as those hailstones fall to the ground, they're mixing with a lot of rain and they're melting quite a bit on their way down. So at the surface, you're just not getting the hail size that MESH is suggesting. So if you want to look at the actual numbers on this day, you'll notice that in general, MESH was too high, almost 2 times too high for a couple of these storms. So the New England storm, it actually, the core of that MESH track did just hit 2 inches, but in reality we were only observing quarter-size hail. And then the same holds true for a storm that occurred later in the day in Emerson, North Dakota. And then it performed better for a cell over Halliday, but there's still hints that maybe it was a smidge on the high side when you look at the max values within those MESH tracks. So as you can see, MESH was trending too high on this day, suggesting hail as large as almost 2.5 inches was occurring. But if you recall the environmental conditions that I showed you earlier, you would want to question that, because the environment really didn't support hail to that size. So now we'll look at a second case study. This was exactly 1 month later in late June. And on this day, MESH actually performed pretty well for storms that occurred really early in the day, even before sunrise for some of those storms. But was far too low for a high-end supercell that moved right over the town of Harvey, North Dakota during the evening hours. So here's how MESH performed on this day. And like I said, you'll see for storms in the morning, MESH was doing pretty well for most of these. Really not doing a bad job, maybe a little on the high side when you're looking at the cores of those mesh tracks. And then what I want you to focus on is this Harvey supercell, where we were observing 3-inch hailstones, even hailstones up to 3.5 inches. So now we're talking hailstones bigger than baseballs. And MESH was much too low. It had hailstones only around 1/4 in size to up to about 2 inches in diameter. So really on the low side there. So I investigated that storm to see, what's going on, what do the radar characteristics look like. And here's the mesh track for that storm, the Harvey supercell. And you'll notice it was depicting hailstones in general less than 2 inches in diameter, except for this really tiny core, few pixels here, where it did get up to 2.1. But that was still about 1.5 inches too low based off what was observed at the ground, which is shown right here. Here's one of those hailstones that was observed at the ground in Harvey, courtesy of Julie Shield, a family member of one of our lead forecasters here at Bismarck, Jeff Shield. So thanks for these photos, Jeff. And here's a picture of the supercell itself, and you can clearly see it had a deep, really well-structured mesocyclone with a nice tilted updraft going on there. So what was the environment like on this day? Well, it looks like we have a stationary front that's pretty much draped west to east across central North Dakota. North of the front, you're in the low 80s for the most part, but south of the front, you're in the upper 80s to around 90 degrees. And then if you look at the Cape and shear on this day, you'll notice, wow, we have an impressive environment on this day. Cape values around 4,000 joules per kilogram over the Harvey area, even higher than that further west. And more importantly, we have some really high shear values, 0 to 6 kilometer bulk shear values in the 50 to 60 knot range over the Harvey area, and even stronger than that a bit further to the north. And not too much going on at 500 millibars, and here we can see our upper level jets kind of up here, up in Canada. So a brief summary of that environment. I would categorize that as a high Cape, high shear day with some weak synoptic scale lift and the presence of some mesoscale forcing along and near that stationary frontal boundary that I showed you a few slides ago. So overall, this was a favorable day for high-end supercells with deep mesocyclones, and given those shear values, you would expect some nice tilted updrafts. So back to our plots, you'll notice on this day, for Cape values as high as they were and shear values as high as they were, we're favoring giant hail that's at least 2 inches in diameter, but possibly up to about 3.5 inches. And based off the work shown in their study, environments like this can produce hailstones even larger than 3.5 inches at times, assuming you have the right storm mode, a nice discrete cell, everything comes together just right, which in this case it did. Here is the supercell that formed just to the west of Harvey and then slowly but surely moved its way right over the town. So I'll let you just watch this loop for a second. And courtesy to Jeff Shield for this loop, he put this together for me, so I really appreciate that. And there you go, you notice the forward flank downdraft moving right over Harvey there. So pretty unfortunate for that town on this day, given those hailstones were really, really giant and caused quite a bit of damage. No tornado, but you had the giant hail. And here's a vertical cross-section of that supercell, and as expected, you can see we do have hints of a nice tilted updraft here with a large overhang area, as you can see right here. And GR2 analyst, surprisingly, which we know is generally too high, that was also too low for this storm. It actually agreed with mesh for the most part, suggesting hail around 2 inches in diameter. So did these dual pole characteristics suggest hail was maybe less than 2 inches or greater than 2 inches? Well, when you see KDP values not displayed like you do right over Harvey in this frame, that's indicative of giant hail greater than 2 inches when you see your real low CC values along with it, which you do right up here. I think values less than 0.9, getting down to 0.84, maybe even less than that in certain pixels. And then ZDR values were also quite low. So you'll notice that if you bring my little checklist back up, you'll notice, yep, we very closely match what you'd expect to see with dual pole characteristics for giant hail that's at least 2 inches in diameter. So looking at all this information combined, you would start thinking maybe mesh is on the low side, and apparently GR2 was as well. So before I get into my last case study of this talk, quick summary. So case 1, we had more of a pulsy air mass thunderstorm type of day, decent cape but weak shear. Storms were more of a vertically upright updraft, and mesh was underestimating on that day. And then case study 2, we had our nice high-end supercell thunderstorm with a deep mesocyclone, a nice tilted updraft, and mesh was underestimating by quite a bit. So here is case study 3, the last one I'll go over with you in this talk. This is from early June of 2019. I know that I said my study only covers 2018, which is true, but I did cherry pick this one case from 2019 just because it really hones in on one of my key findings that I want you guys to remember. So this is another day where we had weak shear, less than 30 knots from 0 to 6 kilometers, but decent cape, around 1,000 to 2,000 joules per kilogram of cape. And it resulted in many marginal pulsy air mass thunderstorms that essentially ended up producing lots of penny to nickel sized hail, but no severe hail. Mesh was too high on this day as well, similar to case study 1. Here's a quick radar loop of this day, and you'll see, yep, we have all of our popcorn-like thunderstorms forming all over, lots of outflow boundaries interacting with each other, occasionally firing up new cells. So yeah, these sub-severe storms are kind of all over the place, but approaching severe criteria when it comes to the hail size, with many of them producing nickel-sized hail, so approaching quarter-sized hail. And then if you look at the mesh tracks for those cells on this day, you'll notice almost all of the cells at some point within their life cycle go up to at least quarter-sized hail, if not even larger than that, approaching hailstones up to 1.5 inches in diameter, including this cell down here. It spikes right up. So if you were to just blindly trust the mesh product on this day, you'd end up with severe thunderstorm warnings all over the place for a quarter-sized hail to, say, half-dollar-sized hail. Problem is none of them would have verified. And we did have a couple of warnings on this day that, like I said, did not verify. And this study helps us realize that maybe in the future we can remember this and remember that storms like this that have these perfectly vertically upright updrafts and have hailstones that are mixing with a lot of rain on their way down often don't end up being the actual size that mesh is suggesting once they reach the ground. And oftentimes these storms end up being sub-severe, at least for our criteria up in Bismarck. So it is worth remembering that these sort of environments, decent cape but low shear environments in which are favorable for air mass thunderstorms. Those are the ones where you have to watch out for mesh being too high a lot of the time. So to summarize my talk, here's my key takeaways that I'd like you guys to remember, if anything, from this study. I would say always be well aware of the environmental conditions and the range of hail sizes that your given environment actually supports. So always mentally have that in the back of your mind. So if you see mesh go haywire, maybe way too high, or maybe you think it's too low, you can maybe mentally adjust for that based off your environmental conditions and what you'd expect based on that environment. And I have created a nice little one-pager to help you determine what a reasonable range of hail sizes could be based on your environment. And that's on the next slide for your reference. And also, one thing I noticed going through all of these cases is that if the max value within your mesh track suddenly increases or decreases, it didn't seem like it was always a good idea to just instantly increase or decrease the hail size in your severe or TOR, especially if the uptick or the downtick in the mesh product was only showing up for just a pixel or two. It seemed like a better idea, one that would work better and lead to better verification results, would be to just wait and see a little bit, maybe another volume scan, to see if that upward or downward trend continues, and if it's for more than just 1 or 2 pixels. And then also, while analyzing your reflectivity heights, your dual pole signatures, in addition to monitoring the mesh product and your environmental conditions. Also, like I said, one thing definitely worth remembering, it does appear mesh is often too high on low shear days that feature decent cape. So for those pulsy air mass-like thunderstorms with vertically upright updrafts. And the opposite holds true for high cape, high shear days, or in other words, days where discrete supercells, high-end supercells are favored with nice tilted updrafts. That's when mesh oftentimes was reading too low. And also, there's some evidence from some of my cases that mesh may be performing poorly on low cape, high shear days. So low top storms, once again, with the tilted updrafts. But I would need to analyze more cases for me to confidently confirm that. So here's that one pager for your reference. I won't go through it. It's kind of self-explanatory, but if you want to try it out for a reference, I find it helpful. So feel free to give that a try this summer when you're dealing with severe weather. And future work for this study would be to extend it to include 2019, so just look at more cases, and then to include the surrounding CWAs as well, once again to increase my sample size and make my results essentially more robust so that I can hopefully get a paper written up that people can use as a reference later down the road. But that's all I got for you guys, so thanks for watching. If you have any questions or comments, feel free to email me at any time at tyler.crans@noaa.gov. Thanks. Bye.